Okay, ready? Okay, I hope it's not too humiliating for you to find the path difference. I hope it's simple enough. The path difference is in meters. How many meters is that? Yeah, 1 meters. Anyone can't get it? Yeah, yeah. So 1 meter path difference. Okay, everyone. Okay.
I wasn't sure what you were asking.
Yeah. So path difference is 1 meter, and are the sources in phase or out of phase?
Out of phase.
Out of phase, exactly. So what happened is that the first maxima over here, the path difference will be half of lambda.
So wait, how do you get path difference?
Because this is 13 meters.
So it's simple.
Pythagoras. Pythagoras. 12 squared plus 5 squared square root, you get 13.
So
13 minus 12, you get 1. So its path difference literally this minus this.
So sir, path difference is defined as from a fixed point and the distance between.
The difference in distance between the sources to the same point.
Okay.
Okay? Now, can you see that the next one, minima, where the path difference is equals to 1 lambda? So the next maxima, the path difference will be equals to 1.5 wavelength. Therefore, you can deduce that if this is a maxima and the third maxima, the path difference must be 2.5 wavelength. Therefore, can you see that I can write this? Nothing, no issues. Okay, no pop-up or whatever.
It's not that yet.
Okay, thank you. Can see or not? First of all, you have to take a look at what's the physical path difference. And this one, you look at the path difference in terms of number of wavelengths. Then you equate the two. How do I know that it's 2.5? You have to count one by one.
So this is what you mean by calculate what you cannot see.
Yes, later on I'll derive an equation that actually allows you to find the wavelength. Not yet, not yet. We're going to use this later on. Very soon. Yes, correct. Kind of like you convert the wavelength into something that you can measure.
I thought the distance.
Everyone okay?
I thought the distance would be 2.5 meters.
2.5 meters?
From the left-hand side.
Yeah, this is 2.5 meters. Agree? Agree. So what about 2.5 meters?
In this expanse of 2.5 meters,
Mhm.
there are 2.5 oscillations.
Okay. So,
So I got
but hang on, you must be careful. We are talking about the oscillation of intensity over here. I'm talking about a wave that is oscillating over here. It's different oscillation then. I'm finding the wavelength of this one. I'm not talking about the wavelength over here.
Oh,
You're talking about the wavelength of intensity variation. I'm talking about the wavelength of the light that causes the intensity, yeah? Now, how is this useful? Let's take a look at this. Next lesson, when we come back, I'll show you variation of this experiment and how it can be leveled up. But for now, let's go functional. Let me show you what is required of IB syllabus. In case you wonder, yes, this is absolutely an IB syllabus. Yes. Huh? How is that possible? I feel so stretched already.
that's a normal question.
Yeah.
Why is this one?
Yeah. Okay. Now let's take a look. Let's consider this angle theta. This is the separation between the sources, yeah? The two sources, the light comes out. Please don't be mistaken that the light only meets here. Actually, the light comes out in all directions. I'm just taking an arbitrary direction, a random direction where the light meets, yeah? Okay, in case you have this idea that how come the light only meets there? So this is distance L. And can you see that if I drop a vertical line, this will be an isosceles triangle. So this is the additional distance that S2 traveled to point X over here. This additional distance. Can you see? Okay with that first? The construction. The construction. That this is the additional distance. So therefore, path difference, which is this section over here, can you see that if this is theta, this is 90 minus theta, hence this is theta.
Sine of d theta.
So this is d sine theta. Yes, correct. Now, I'm going to show you something, but I'm not going to assume that you know it. So I'm going to show to you what I'm going to assume. Opposite, hypotenuse, adjacent, theta. Sine theta, this I have to assume that you know. Tan theta, this I have to assume that you know.
What a bold assumption.
When theta is
You
small,
never know.
when theta is small, do you agree that adjacent is approximately equals to h? Make sense? Therefore,
yes.
tangent theta is approximately sine theta. No, approximately sine theta.
Yeah.
Because if this is approximately this, then this should be approximately this.
Which are both close to 0.
Yeah, that doesn't matter. We cannot put 0 equals to 0, then it's meaningless. Yeah?
Right, relative.
Yeah. So what you have over here now is that d sine theta becomes d tangent theta.
Wait, sir, what? Okay.
When angle is small, if theta is small.
But it doesn't look very small.
Exaggeration. I can't possibly draw like this, right? Can you see the right angle triangle or not? You can't, what? I have to exaggerate a bit. So if I call this x and this being L, can you see that tangent theta is equals to x upon L?
Which is 0.
This is x. I didn't say anything is 0. when did I say anything is 0?
It's not 0.
You have been the one saying that it's 0, 0, 0, 0, 0, 0, 0. No, I didn't say 0. All I mentioned was this and this. That's the thing that I jumped. Where is the 0? Still here? Still here? Okay. Now, for constructing interference, path difference must be equal to? Whole number, yeah, okay, n lambda, right? Therefore, the x positions where the bright spots are is given by this. Now, what does this mean? It means that x can be equals to L lambda upon D, can be 2L lambda upon D, can be 3L lambda upon D, and so on and so forth. So the separation between the adjacent bright spots will be this. And this was what Young's, the scientist Young's modulus, Young's double slit, Young's, came up with, which is a method for you to determine the wavelength of light.
What a genius.
Yeah. Can this be measured? Absolutely. It's in the order of 2 meters, 1 to 2 meters. Slit separation, at that point of time, you just have to take a cupboard, cut 2 very narrow slits, yeah, which you can measure the separation. And then X, usually in the order, when you do experiments, is usually in the order of a few mm.
So can you do physics here on this?
Yeah, I think it'll be a D. Because what the definition of E is that it has to be something that's out of your syllabus. D sine theta is the path difference, which is what I mentioned over here. Yeah. So essentially, what do you have to know? The equation over here. Or this form. Is this form or this form? Either form. I mean, it's the same. Very important part over here. Very important part over here that you need to know is that listen, hello. Important. Otherwise, you're going to be lost. The very important thing over here is that the intensity, the regions where you have the bright spots is going to look like this. Relax. This simply means that this is bright, this is dark, this is bright, this is dark. So what you see on the screen is not like some undulation, as in like it's not going to protrude out or going down. It's just going to be bright, dark, bright, dark, bright, dark. Because this is the screen. Yeah, because this is the screen. This is the intensity, this is the position X.
So it's narrow strips?
Yeah, you see bright, dark, bright, dark, bright, dark, bright, dark. They are evenly spaced and they are evenly bright. Are your brain fried already?
Still trying to digest that L over D thing.
I guess it hasn't blown out yet. Has the recording?
It is.
It is still recording, or it is? It is. Okay, good, excellent. So HD is good. Okay, quick summary of this section. Then I'm going to do a quick summary of the whole thing today. Cool? Then in much of a sadness, I have to let you go. Okay? Listen, consolidate. 5 more minutes. 5 more minutes and you go. What we have over here is what we call the Young's double slit experiment. Very important experiment. I'll explain to you why. And listen now, hello. How many times must I do this? So path difference is equals to d sine theta, and then from there I derive the expression based on the idea that the angle theta is small. Very important part. I will show to you what happens when the theta is not small. It will deviate from what we expected. So if the theta is small, you're going to see a pattern that is evenly spaced, bright strips that are evenly spaced, bright fringes that are evenly spaced and evenly bright, and the separation between the bright spots or bright regions are given by this expression. Powerful formula because and powerful phenomena because whatever you throw over here, if it shows bright dark, bright dark, bright dark, you know that whatever you throw at the two slits is a wave. And this is the part that I'm going to leave with you, a kababoom kind of thing to think about. Scientists in the past, or scientists not too far in the past, in the distant past, not in the distant past, they threw electrons at these two slits. Yeah, electrons one at a time. And then they realized that electrons also show this. Yeah? And basically electrons behave as wave. And if you don't know, electrons is one of the only particles that we don't have the size of the particle. We don't have. Nucleus we have 10 to the power minus 15. Atom we have 10 to the power minus 10. Yeah? We don't. It's as of now, electron is a point mass. It's just bombing any equations that you just Heisenberg, everything. Okay. Yeah. Okay. What about? What about? Yes. What about? But hang on. How can you have a particle that doesn't have a size? How do you exist? You must occupy space, right, to exist. It really challenges the notion of existing there. How can you exist without occupying a space? Anyhow bomb again. Dark matter are WIMPs. Yeah. By the way, WIMPs are weakly interacting massive particles. Okay, you think what are WIMPs? Weakly interacting massive particles. Okay, can you just press stop over there? Thank you.